All right, strap in, everyone, because today we're taking a deep dive into the world of antimatter.
Oh, yeah. This is going to be a fun one.
It's one of those topics that sounds like it's straight out of science fiction, but it's actually a fundamental part of our universe.
It really is, and it's mind-boggling when you start to wrap your head around it.
So let's start with the basics. What exactly is antimatter?
Well, you can think of it as the evil twin of regular matter. Every particle of matter has an antimatter counterpart with the same mass, but the opposite charge.
So like a mirror image, but with a twist.
Exactly. A perfect example is the electron, which has a negative charge. Its antimatter counterpart is the positron with a positive charge.
Okay, I'm starting to get the picture. So every particle has its opposite, like a cosmic balancing act.
Right. And we're not just talking about electrons. Protons and neutrons also have their own antimatter twins, antiprotons and antineutrons. It's like the universe has this built-in symmetry.
So what happens when these matter and antimatter twins meet? Do they just cancel each other out?
Well, cancel out is a bit of an understatement. When matter and antimatter collide, they completely annihilate each other.
Annihilate. Wow, that sounds intense.
It is. And the crazy thing is, all of their mass gets converted into pure energy during this annihilation process. It's a 100% efficient, following Einstein's famous equation, E mp.
Energy wasted. Talk about efficient. I can already see why scientists are so fascinated by this stuff.
Oh, absolutely. That kind of energy release has incredible potential, but we'll get to that later.
For sure. But before we dive into the what-ifs, I'm curious about how we even discovered antimatter in the first place.
It's a pretty amazing story, actually. It all started with physicist Paul Dirac back in 1928. He was working on some groundbreaking theoretical equations, and he predicted the existence of antimatter before anyone had even observed it.
Wow, so it was pure theory at that point.
Yeah, pretty bold prediction, right? And it took a few years for experimental evidence to catch up. But in 1932, Carl Anderson was studying cosmic rays, those high-energy particles bombarding Earth from space.
Right, those are still a bit of a mystery themselves.
Totally. Anyway, Anderson observed a particle behaving like an electron, but curving the wrong way in a magnetic field.
The wrong way. What does that mean?
Well, it meant the particle had a positive charge, which was totally unexpected. He had discovered the positron, the antimatter counterpart of the electron.
So direct prediction was right. That must have been a huge moment for physics.
Absolutely groundbreaking. It opened up this whole new realm of antimatter research that's been going strong ever since.
So if antimatter is found in cosmic rays, does that mean it's just floating around out there in space?
We do find trace amounts in cosmic rays, and it also shows up in some radioactive decay processes. But to create substantial amounts of antimatter, we need something a bit more powerful. We need particle accelerators.
Like the Large Hadron Collider, that massive machine that smashes particles together at incredible speeds.
Exactly. By smashing particles at those super high energies, these accelerators can create particle-antiparticle pairs. You could almost say it's like splitting the atom in reverse.
That sounds incredibly complex and probably expensive.
Oh, incredibly so. To give you an idea, producing even a tiny amount of antimatter, like a fraction of a gram, can cost billions of dollars. It's a very energy-intensive process.
Okay, so we've established that antimatter is real. It annihilates with matter in this incredible energy release, and it's really difficult and costly to make. But here's a question that's been bugging me. If the Big Bang supposedly created equal amounts of matter and antimatter, shouldn't they have just annihilated each other right then and there?
Yeah, that's a great question, and it leads to one of the biggest mysteries in physics, the baryon asymmetry problem.
The what problem?
Baryon asymmetry. It's the observation that our universe is dominated by matter, not just an empty sea of energy, which is what we'd expect if matter and antimatter were truly equal at the beginning.
So something must have happened to tip the scales in favor of matter.
You got it. Baryons are the building blocks of matter protons and neutrons. And we observe way more of these baryons than we should if matter and antimatter were perfectly balanced in the early universe.
Okay, so there's this cosmic imbalance that we can't fully explain. What are some of the theories out there trying to solve this puzzle?
Well, there are two main contenders. One is called CP violation, and it's the idea that particles and antiparticles might behave slightly differently in certain interactions. These tiny differences over billions of years could have led to matter accumulating while antimatter slowly faded away.
So even the tiniest difference could have had massive consequences on a cosmic scale.
Precisely. The other theory dives into the very early universe right after the Big Bang. It's called asymmetric inflation, and it suggests that during that period of super rapid expansion, the conditions somehow favored the creation of slightly more matter than antimatter.
So two very different ideas, but both trying to explain this fundamental mystery of why we exist at all.
Exactly. And that's what makes antimatter research so captivating. It's not just about the practical applications, but about understanding the very fabric of our universe and how we came to be.
I'm already hooked, and we've only just scratched the surface.
Oh, there's so much more to explore, trust me.
I believe you. But for now, let's shift gears a bit and talk about those potential applications of antimatter. I mean, the idea of harnessing that energy is pretty mind-blowing. What could this technology unlock if we can figure it out?
Well, when you think about the sheer energy potential of antimatter, I mean, it's hard not to let your imagination run wild.
Oh, for sure.
And one of the most exciting possibilities that always gets people talking is space travel.
Yeah, antimatter rockets, it's straight out of Star Trek.
Right. But imagine a rocket powered by matter-antimatter annihilation. We're talking about insanely efficient propulsion, enough to explore the vast reaches of space, maybe even travel to other stars.
Okay, now that's a thought. But let's be realistic for a moment.
Uh-huh.
How feasible is this, really? What are the challenges in turning this sci-fi dream into a reality?
Well, the biggest hurdle, by far, is containment.
Makes sense. I mean, we're talking about incredibly volatile stuff here.
Yeah, antimatter annihilates instantly on contact with regular matter, so storing it in the typical fuel tank is out of the question. We can't let it touch anything.
So how do you even begin to contain something like that?
Well, scientists are working with incredibly powerful magnetic traps, trying to suspend antimatter in a perfect vacuum.
So it's like suspending a tiny bomb that could go off at any moment if it touches anything.
It's a pretty intense challenge, to say the least, and these magnetic traps require a tremendous amount of energy to maintain, so it's not exactly a simple solution.
Sounds like we're still a ways off from building those warp drive starships.
Probably, yeah. But hey, if we can eventually figure out nuclear fusion, maybe antimatter containment is the next frontier.
Fingers crossed. But in the meantime, are there any more immediate down-to-earth applications of antimatter? I've heard it's already being used in medicine, which is pretty amazing.
It is. Positron emission tomography, or PET scans, use antimatter in a really clever way to image the body. It all comes down to those positrons we were talking about earlier, the antimatter twins of electrons.
PET scans, right? So we're talking about those scans that give doctors those really detailed 3D images of our organs and tissues.
Exactly. So in a PET scan, the patient is injected with a very small amount of a radioactive substance that emits positrons.
And because positrons are antimatter, I'm guessing they don't last very long in our matter-filled bodies.
You got it. These positrons travel a short distance within the body before encountering an electron and boom, annihilation.
But instead of a massive explosion, we're using this process to create images.
That's the brilliance of it. The energy released during annihilation produces gamma rays, which can be detected by special scanners. By analyzing the patterns of these gamma rays, doctors can create those detailed 3D images, helping to diagnose and monitor all sorts of conditions.
So it's like we're harnessing this incredibly destructive force for a beneficial purpose.
It really highlights the dual nature of antimatter. It's both this source of immense destructive power and a tool for scientific understanding and advancement.
And speaking of potential, let's talk energy production. I mean, if antimatter annihilation is the most efficient energy conversion process in the universe, could we, use it to power our cities, maybe even replace fossil fuels completely?
The idea is incredibly tempting, right? Theoretically, a tiny amount of antimatter could generate a massive amount of power. We're talking about potentially powering entire cities with just a few grams of the stuff.
That's incredible. So what's stopping us from building antimatter power plants?
Well, as we've discussed, those production costs are astronomical. It's not exactly a cost-effective energy solution with our current technology. And then there's the whole containment issue. Safely storing and handling large amounts of antimatter is a challenge we haven't overcome yet.
Right, that makes sense. It's like trying to bottle lightning. Incredibly powerful, but also incredibly difficult to control.
Exactly.
So it sounds like antimatter power plants are still a distant dream for now.
I'd say so.
But even if those practical applications are a long way off, I'm guessing the research itself is incredibly valuable. What are scientists learning from studying antimatter, even if we can't use it to power our homes just yet?
You're absolutely right. Antimatter research is providing us with a unique window into some of the most fundamental mysteries of the universe. By studying antimatter, we can learn more about the nature of matter itself, the origins of the universe, and potentially unlock new laws of physics.
It's like antimatter is this key that unlocks deeper levels of understanding about the universe.
It is. It's a journey of discovery with implications far beyond any specific technology.
Okay, so we've covered a lot of ground here, from the mind-boggling concept of antimatter to its potential applications and the immense challenges we face. What are some of the biggest obstacles facing antimatter research today? Where do we go from here?
Well, besides the cost and containment issues we've already talked about, the sheer complexity of working with antimatter is a major hurdle. It requires some of the most sophisticated equipment and the brightest minds in the world to even conduct these experiments.
I bet it's not easy to find people who specialize in antimatter physics.
It's definitely a highly specialized field, but thankfully there are leading research facilities around the world pushing the boundaries of antimatter science.
Like where? What are some of the places where this cutting-edge research is happening?
Well, CERN, the European Organization for Nuclear Research, has a dedicated facility called the Antimatter Factory, where they're doing some incredible work. And then there's Fermilab in the United States, another powerhouse in the field, making significant contributions.
I'm always amazed by the global collaboration in science. It's really inspiring.
It is. And what's really exciting is that these researchers are constantly pushing the boundaries, asking those big questions that could revolutionize our understanding of the universe.
So what are some of the big mysteries they're trying to solve? What are they hoping to achieve through this research?
One of the most fascinating areas of research is the study of antihydrogen, the simplest atom of antimatter.
Antihydrogen, so that's a positron orbiting an antiproton, right?
Exactly. It's like the mirror image of a regular hydrogen atom, which, as you know, is the most abundant element in the universe. And by comparing the properties of hydrogen and antihydrogen with incredible precision, we could potentially unlock the secrets of that fundamental asymmetry between matter and antimatter. Why is our universe dominated by one and not the other?
Wow, so we're talking about potentially answering the question of why we even exist at all.
That's the ultimate goal. It's not just about cool gadgets and futuristic technology. It's about understanding the very essence of our existence.
I think I need a moment to process all of this. This has been an incredible journey into the world of antimatter. It's clear that even though it sounds like something out of science fiction, it's very real, and it has profound implications for our understanding of the universe. What are some key takeaways you want our listeners to walk away with?
Well, I think the biggest takeaway is that antimatter, despite sounding like something out of science fiction, is a very real and fundamental part of our universe.
Yeah, it's definitely not just a figment of our imagination.
Right, and this stuff is the mirror image of the matter we interact with every day. It has all the same properties, but with the opposite charge. And the craziest thing is that when matter and antimatter come into contact, they annihilate each other in this burst of pure energy.
It's that energy release, I think, that really captures people's imaginations. I mean, the potential applications for things like space travel and energy production are mind-blowing.
They are. But as we've discussed, the challenges of producing and containing antimatter are immense, at least with our current technology. It's incredibly difficult and expensive, like trying to harness a force of nature that's both incredibly powerful and incredibly volatile.
So it sounds like those sci-fi dreams of antimatter-powered spaceships and cities are still a ways off. But even without those immediate practical applications, it seems like the research itself is incredibly valuable.
Oh, absolutely. Studying antimatter is giving us insights into the fundamental building blocks of matter, the origins of the universe, and perhaps even the laws of physics themselves. It's a journey of discovery with the potential to lead to breakthroughs we can't even imagine yet.
It really feels like we're just scratching the surface of what we can learn from this stuff.
We are, and that's what makes it so exciting. It's like antimatter is this key that can unlock a deeper understanding of the universe and our place in it.
Well said. This deep dive into the world of antimatter has been truly incredible. We've explored its mysteries, its potential, and the amazing scientific endeavors underway to uncover its secrets. It's clear that antimatter is more than just a scientific curiosity. It's a window into some of the deepest mysteries of our universe. Any final thoughts you want to leave our listeners with?
You know, I think the biggest thing I'd want people to take away from this is that sense of wonder and curiosity about the universe. The universe is full of mysteries waiting to be explored, and antimatter is just one example of how science is constantly revealing the strange, the beautiful, and the incredibly complex nature of our existence. So keep exploring, keep asking questions, and never lose that sense of awe.
That's perfect. A huge thank you for joining us. and for guiding us through this incredible deep dive into the world of antimatter. It's been an absolute pleasure.
It's been my pleasure. And to our listeners, thank you for joining us on this journey.